In my last videos, I presented an outline of a filtration system designed to address the film issue from my boron printer. Today, I will provide more details about the electrical sensors and discuss an additional features I envision for the filtration system. Hi, welcome to Slow Engineering. I'm David. In the previous episodes, I mentioned my plan to monitor the HEPA and carbon filters using pressures and VOC sensors. I positioned one set of sensors at the inlet of the filtration system and the other set at the outlet. The HEPA filter is clogged if the pressure drops significantly from the initial setup. The VOC sensors are more straightforward. If the sensors at the outlet detects high pollution levels, it signals that the carbon filter needs to be replaced. I've discovered that the VOC and pressure sensors modules use I2C for communication. I connected them to a microcontroller board and a small display to test their functionalities. I use a soldering iron to remove the heated insert from an ABS print. Additionally, I have another air monitoring device that cannot detect ABS fumes. I have already researched multiple sensors, which do not show they can detect ABS fumes. Before I removed the inserts, the index values was around 100. After heating and attempting to remove the inserts, the index value increased. This indicates that the sensors are responsive to ABS fumes, which is a positive sign. Do the VOC come from the iron or the melting ABS? I conducted another experiment with the 3D printers to investigate further and check the sensors that detect the melting ABS. I placed the sensor inside the 3D printer enclosures and melted the filaments using the nozzle. After pouring on the sensors, I initially allowed them to learn about the environment. The small display provided readings for the inlet and outlet, VOC levels, pressures, temperatures, and relative humidities. The readings stabilized at around 97 or 98. After some time, I began extruding the ABS filament, and the index values increased slightly to 102 or 103. This indicates that the sensors are still capable of detecting the fumes. I added a frequency converter to the system as a new feature. In my previous build, I attempted to control the PWM exhaust fan using my 3D printer's mainboard. Unfortunately, I was mistaken. The mainboard cannot control the fan through PWM. As a result, I could only regulate the fan speed using voltage, which limited its operational range. After acquiring an oscilloscope, I measured the mainboard's PWM frequencies and found it outputs 100 Hz. In contrast, standard PC PWM fans operate at frequencies between 22 kHz and 28 kHz. This difference in frequency is why I couldn't control the fan using my 3D printer's mainboard. However, I can fully control the fan through the mainboards by implementing a converter that can change the low frequency output to a frequency that a regular PC PWM fan can accept. I researched the mainboard schematics and discovered that the pinout positions doesn't correspond to the common grounds I initially assumed. The positive pins for the fan is directly connected to the power source, which provides 5V. A MOSFET controls the negative pin, connecting it to the ground to allow current to flow from the positive to the ground. thus generating PWM signals. This setup complicates the connections to the converter due to the lack of a shared common ground. I added a pull-down resistor to the ground at the converter input to address this issue. These connections will serve as reference ground for the mainboard output. According to the schematics, I only need to connect the negative pins to the converter input. When the MOSFET is off, the current flows from the positive terminal through two resistors and the LED to connect to the ground. This action generates a high level of the PWM signal. Conversely, when the MOSFET is on, the current flows directly to the ground, resulting in a low level of the PWM signal. This setup creates a PWM signal with a reference ground on the converter side. It's important to note that the PWM signals will be inverted compared to the original standard connection. However, reversing the signal in Clipper is straightforward. Due to the connection through an internal 4.7K ohms resistor and an LED, the voltage at the negative pins is no longer a 5V PWM signal. I tested various resistor values to obtain a signal that the microcontroller can read directly, which accepts a 3.3V PWM input. Ultimately, I settled on a 47K ohms resistor to meet this requirement. These are the primary features I plan to apply to the filtration system. What are your thoughts on them? Do you have any suggestions or ideas for additional features? Please leave your thoughts below. As always, moving forward.